for today. So first of all, let's review the definition of beats. So we learned the beat from the undamped, harmonically excited systems. So a typical beat profile is shown in these plot. So this plot is called beat, and then you can see the x-axis is time, y-axis is displacement. And then the first question we need to ask is when we usually see beats. So in the class, we actually talk about two different cases. So that's here I show the equation for case 1. So if you don't remember, so the case 2 equation is actually x double dot omega n squared x equals to f naught times psi omega t. So the only difference is the right-hand side, what's on the right-hand side. So case 1 is cosine function, case 2 is sine function. So for the case 1, when we have all 0 initial conditions, that's the condition where we need to get the beat profile. And then if we have the beat, then we can use these time domain function to describe the profile of the beat. So actually it has 3 components. The first component is here, which is the amplitude. The second component is here, is a high frequency oscillation. Let me name it oscillation. And then the last component is actually a low frequency oscillation. So how should I name it? Let's name it as low frequency. So why this is high frequency is because you can check the frequency component. The frequency for this oscillation is omega n plus omega. So that's a really large number. So here, this is a very small number. That's why it's low frequency. So let's try to find all these 3 components from this plot. So first of all, we can easily find the high frequency oscillation, right? Because we just focus on one period of the high frequency oscillation. Let's see, you can find 2 consecutive peaks. And then the distance between these 2 peaks, we call it the period of this high frequency oscillation. And then once we have period, we already know that period is omega over 2 pi over omega, right? And then what we also name this omega as oscillation radial frequency. So this omega oscillation equals to 2 omega n plus omega, which is this number. That means the high frequency profile in this plot is due to this high frequency oscillation. So that's why you can directly connect this period to the high frequency oscillation. So the second part we need to find is amplitude. So where can we find this amplitude? So in order to find this amplitude, we have to look at this amplitude together with this low frequency component. We can assume, so we can see that this amplitude is actually the amplitude of this low frequency component. So where's that low frequency? So if you go to these plots and connect all these peaks, this green line is actually the low frequency component. And then from there, we know that this low frequency component has an amplitude. That's our amplitude. So which means the peak of this dashed line is actually the coefficient here. Okay, so how about the last part? The low frequency oscillation. So we already know that So I think during the class, I already mentioned that we have another definition, which is the, you can draw another profile, which is something like this. Right? So these two dashed lines, they are the envelope for the beat profile. So that means your beat can never go beyond these dashed lines. So what we can do is actually we can measure the distance between these two numbers. This distance is called period of beat. And then period of beat is actually omega beat 2 pi over this. And then by definition, omega beat is the absolute value of omega n minus omega. You can see that the omega beat is not half of omega n minus omega. That's because your beat period is the distance from peak to the valley. It's not the distance from the first peak to the second peak. So that's why it's only half of the low frequency oscillation period. So that's something you need to pay attention. And then the other thing you have to pay attention is your omega beat is actually the absolute value of the difference. So that means in your final solution, you usually see two solutions. So I believe you already see these from seen this from your homework 1. Okay, so that's for the beats. So any questions? So, all right, so I'm gonna move to the second page. All right, for the second page, we already did part of the work during class. So for the question 1, I'm gonna just directly write the equation of motion for you. Okay, so once you have the equation of motion, so we want to connect this to the standard format we usually see. So the standard format is omega n. The standard format is actually theta double dot to omega n zeta theta single dot plus omega n squared equals to f naught cosine omega t. So we want to convert the first equation back to the standard equation so we can apply all the all the transfer functions we learned during class. So what is omega n? Your omega n is simply square root of k over m. If you don't recall what the k and m is, so k is whatever coefficient in front of theta. And then m is whatever coefficient in front of theta double dot. And then, of course, in this case, your c is whatever coefficient in front of theta single dot. So in order to avoid confusion, let's name it as c prime here. Okay, so omega n is k over m square roots. So that's going to give you a number, which is 5 radian per second. And what other stuff we can find? So we need to find zeta. Okay, zeta is, according to definition, is c prime over 2 square root mk. So we know m, we know k. C prime is a function of c. And then according to the definition, the damping ratio is 0.2. So from these equations, you can get the c number is 163.265 kilogram per second. And then we know omega n zeta, the next one is F naught. So your F naught is the big amplitude, F, divided by the mass. So your F naught is -1, it's a -1 Newton, and then your mass is 0.4. So that's going to give you -2.5, the units Newton per kilogram. And then what is omega? Omega is simple, it's directly 10 radian per second. Okay, we have all this information, then we can progress the part 3. Okay, so let's read part 3, because usually when we talk about steady state amplitude, that means we usually need transfer function. So if we need transfer function, we need to find what the output is and what the input is. So in this case, the input is easy. The input is the force applied to the system. And then the output, in this case, the output is the angle theta. So that's the theta. We want to check what's the maximum theta amplitude in this frequency range. So that means your output should be theta. And then to find the relationship of these, we need to find the transfer function. Okay, so what's the transfer function here? It's pretty straightforward. We just do Laplace transform on both sides, and you're gonna have S squared 2 omega n zeta S plus omega n squared. That's 1 on top. Okay. So once you see a transfer function like these, I would suggest you to go back to your notes and find where you have seen this before. So in this case, it's displacement divided by force. That's definitely compliance. So you need to find the compliance transfer function in the in your notes. That is, where is it? I think that is in lecture 8, slide 5 and 6. So we would like to plot the shape of this transfer function. So if you recall, the shape of the transfer function is, so we use a relative frequency ratio R, and then the amplitude of this transfer function. And then the shape is something like this. So the reason why I draw peak here is because the damping ratio is 0.2. As we discussed before, the peak is gone when zeta is greater than 0.707. So it starts from 0, peaks somewhere, and then decays afterwards. So where the peak is, that's the R peak. If you recall, this R peak is square root 1 minus 2 zeta squared. That's all in your notes. And then if you put zeta equal to 0.2 in your equation, you would have this R peak equal to 0.9592. So that means your transfer function peaks at this R value. So let's see what is the range of our input R. So in this case, let's recall the definition of R. The definition of R is excitation frequency over the natural frequency. Okay, so natural frequency is 5, and then the excitation frequency ranges from 1 to 9. So that means your R is in the range of 1/5 to the range of 9/5. So that means if you plot your R range in these plots, your R is somewhere in here. Your R covers this red range. Okay, so if your R covers this red range, definitely we know the maximum steady state amplitude is the peak, right? That means when R peak when r equals to 0.9592, you have the maximum steady state amplitude. If that's the case, that means your omega is, let's see how much it is, 5 times this number. That's about 4.9 or something. That's 5 times 0.9592 radian per second. So which means if I give you a frequency range and I ask you to find the maximum value of this transfer function, then what you need to do is you actually need, I think the best idea is to draw this body plot and then find the frequency range in the body plot and then manually find that peak. So for example, I can easily change this question. For example, what if your omega range is not from 1 to 9? What if your omega is from 9 to 10? Then what is your range? So what is the peak number then? So in this case, if it's 9 to 10, so your R is actually from 9/5 to 10/5. So it's from 1.8 to 2. So 1.8 to 2, it doesn't cover this R peak range. It's actually bigger than this R peak. So in this plot, what you need to find is actually this range, right? So in this case, your steady state amplitude peaks when your R number is the smallest. So that means if this is the case, your maximum amplitude occurs at R equals to 9. I can also give you another range. What if your omega is from 0 to 0.5? You can think about these after this online session. Because if you look at this omega range, you can figure out that your omega never covers your peak and is always to the left-hand side. That means these values going to give you the maximum amplitude. So that means in order to calculate the maximum amplitude, you first need to draw the body plot. The second thing is you need to find the range of your R and then plot this range of R in your body plot and check if the peak is covered in this range. If it's not, then usually the maximum amplitude occurs at the boundary. So if there is a peak in the center, that means the maximum amplitude is at the peak. So any questions? Okay, I'm gonna move forward. All right, that's another homework question. So it's a spring mass damper system with a harmonic force applied. So the first thing we can do is directly write the copy and paste the transfer equation of motion from the lecture notes. Okay. So again, we don't like these formats. We want standardized format. But we can easily find this information from K, M, and C values. Your natural frequency is square root K over M. Your zeta is C over 2mk. Then you can easily calculate this number. Let me see. Omega n is 132 radia per second. Your zeta is 0.0085. Okay, so the first part of this question is we need to calculate the steady state response. In this case, because we haven't talked about velocity acceleration in lecture 8. So in this case, the steady state response is the displacement only. And your excitation is 132, which is exactly the resonance. So we need to calculate what that X amplitude is. So because we need to calculate the X amplitude, so we need to find the transfer function again. So we need to find the transfer function amplitude. And then as we can recall, is 1 over S squared 2 omega n zeta S plus omega n squared. And also, you can find another format from the textbook is 1 over, so let's see, that's the norm of this. And then you can also find another format which 1 minus R squared plus 2 zeta R squared. And there's another, okay, you have a K on top. You can find this equation from your next lecture notes. And then if you directly use this equation, so what you can do is just directly find your R values. Your R equal to omega over omega n. And then that's directly 1 in this case. You can plug this R equal to 1 back into this equation, and then that get the F, X over F ratio. If you don't remember why we get this equation, the other thing you can do is you directly can replace your S by omega J, right? So your S domain expression becomes a complex number. So S squared is omega J squared. It's minus omega squared. You remember to put this minus sign there. And then we have, in the denominator, we have omega n squared minus omega squared plus 2 omega n zeta omega j. So the amplitude of these complex number, there are 2 ways you can do it. So if you bring MATLAB to your exam, so you can directly use norm function. You put this complex number inside this bracket, and then this norm function is going to give you the amplitude. If you don't have MATLAB, what you need to do is just simply calculate it by hand. It's going to be square root omega n squared minus omega squared. The square of the real part plus the square of the imaginary part, and then take the square root and put a 1 on top of it. So that's also a solution for the ratio of X over F. So that means you have 2 ways to calculate the amplitude of this transfer function. You can either find the right equation from your lecture notes, or you can use the definition for body plot. Just replace S by omega J. Eventually, you're going to get the same solution. But what I'm asking here is not the ratio, it's actually the steady state response. So in order to transfer it to X amplitude, you have to multiply this ratio by the amplitude of your force. And then this amplitude of force is not directly given. We only have F naught. We have to time it by the mass to get this F amplitude. Remember, this small F naught, that's mass normalized force. So you can check the unit, it's Newton per kilogram. So that's why we have to multiply the mass back to get the actual force amplitude. Okay, so that's the 3rd question. Any comments or questions? Okay, so I'm gonna explain the norm. So the norm, so there are actually, so mathematically, the best way to define the norm is when you have a vector, you have vector, right? Let's say this V is a vector. the norm of a vector is the length of the vector. So let's see if you have a 2D vector, if x or y, this vector is something like this. That's your v vector. So the length of this line is called the norm of the vector. So if it's for a complex number, so we change the xy coordinate to real and imaginary, right? So your vector is no longer vector, it's actually a phasor. So, but then the definition for norm still stands. So the length of these phasor is the norm of the complex number. So v becomes a complex number. So the norm of this complex number is this. We still use the absolute value symbol, but it's named as norm. So this length is actually, you have your real part, you have your imaginary part, right? So the length here is real part square plus imaginary part square, take a square root, right? Because that's a triangular, that's a perpendicular here. So yeah, so to make it simple, so the norm is actually the length of the vector. And then the norm for a complex number is the length of the complex number, is the length of the phasor in complex domain. Okay, so let's move forward. Oops. All right, so we have, that's for lecture number 9, homework 1. So since we learned a lot of stuff, at the end of last lecture, I summarized all the systems we learned. So we actually have learned 4 different systems. So we applied the force, we applied base excitation, we applied unbalanced rotation, and then we choose different inputs and outputs. So the first thing you need to do is when you see a question, you need to determine which system that is. Like for example, in this case, we see a machine, we see the machine is sitting on a mount, and the mount is fixed to the floor. But then the floor is actually vibrating. So we know that's a base excitation problem. So that means your input, in this case, is YT. Once you have this basic idea is base excitation, then you can directly copy and paste the transfer function, the equation of motion from the lecture notes, right? That's the equation of motion, and then the displacement of your machine mass, that's your x. And if you don't like this way, you can also write it in the standard format, convert everything to omega and zeta. Okay, so let's read the equation. Let's read the problem description. So the machine is weighing 2,000 Newton. So that big mass has a gravity of 2,000 Newton. When it's resting on the support, it gives you a data static deflection. So when it's resting, that means the deflection is all due to the deformation of your spring. So that's why the gravity divided by the stiffness is the static deflection. So we know in this way we can get the K value is 2,000 Newton divided by, where is it? Okay, the deflection is 5 centimeter. So that gives you 40 K Newton per meter. So that means from here we can get the stiffness of your support, which is a K value. Beyond that, what we're having. So we know the system is oscillating harmonically near resonance. So the word harmonically indicates that we can use transfer function. And then when it's near resonance, we know R equals to omega over omega n equals to 1. And then we know the amplitude is 0.2 centimeter. So we know the amplitude of X is 0.2 centimeter. And also this gives us the system damping ratio, 0.01. Okay, so because it gives us this X displacement, that means it's better for us to choose your X as output, right? Wait, I think this is not X amplitude. I had it wrong. So that should be the Y amplitude. Oops. Because that's the base excitation amplitude. So that means we have to choose this Y as our input. So if in the exam, if I give you the base velocity or base acceleration amplitude, then you should be able to change these accordingly. So we know the base inputs, and then what we need to calculate. We need to calculate the transmitted force, and we need to calculate the transmitted displacement. That's your transmitted force, transmitted displacement. So there are several things you can do. First of all, your transmitted force over Y. We already have the transfer function, right? If you go back to your notes, you can find this transfer function. Usually we write it as function of R. And then we also have this displacement transmissibility. So you can directly find this information from in lecture notes. If you don't, so if you're not 100% sure which transfer function to use, then you can go, again, you can go back to the definition of transfer function. Like, for example, I can take the displacement transfer function, for example. X over Y, directly doing Laplace transform. It gives you S squared plus 2 omega n zeta. S plus omega n squared. On the numerator, you have 2 omega n zeta squared. Oh, sorry, zeta S plus omega n squared. By doing Laplace transform of these equations, you can get the transfer function. In order to calculate the body plot, you just replace your S by omega J. So let's see what's happening. So you have 2 omega n zeta omega J plus omega n squared. You have omega n squared minus omega squared plus 2 omega n zeta omega J. So again, inside these absolute value symbol, you have a complex number. Right now, you have to calculate the norm of this complex number. So you can, again, you can use a norm function in MATLAB. If you don't know how to do it, if you recall the norm definition we have, it's just the square root of the real parts plus the square root of the imaginary part. Sorry, it's let me see. You mean the Laplace transform function here needs to be flipped? Let me see. I don't think so. So if you don't remember how to do this Laplace transform exactly, so I can start from the beginning. So let's focus on this equation. So on the left-hand side, x doubled up becomes s squared xs. The second term is 2 omega n xi s xs plus omega n squared xs equals to CSYS plus, sorry, I copied the wrong equation. That should be 2 omega n xi s, zeta s, and then omega n squared ys. So you can collect terms. So you can move all these ys to the left-hand side. So 2 omega zeta s plus omega squared, they should stay on top, and then they're on the right-hand side. That's where they are. And then the coefficients for xs, they move down to this vector. So does that answer your question? Is it for this one? So here, let's write it out. You have x s over y s. So if you multiply it back, you can see these give you these two equations are equivalent, right? Okay, cool. So you can directly calculate your displacement from here. So what you can do is we know omega n, we know omega, and we know zeta. You just plug all this information back into the expression, and then you get the ratio between x amplitude and y amplitude. And we already know y amplitude, and then you just multiply this amplitude by the ratio, you get the x amplitude. Okay, so in the lecture notes, we use this r value a lot. So how do we get this r? If you don't remember, then what we do is you divide both the denominator and the numerator by omega n squared. So your denominator becomes square root 2 zeta r squared plus 1. And then in the denominator is 1 minus r squared plus 2 zeta r squared. So that's your lecture notes. If you don't know, if you're not 100% sure about your lecture notes, then I think the best idea is just start from the transfer function, replace your s by omega j, and then get this complex number, and then calculate the norm of the complex number, and then you will get us the same solution. And then I believe these actually works, actually can avoid mistakes. Because if you choose the wrong transfer function at the beginning, and you plug the r into the wrong transfer function, you're going to get the wrong solution. If you directly start from the transfer function, then you actually have less chances of making mistakes. Okay, so that's homework 1 in lecture 9. So I think I can move forward. Okay, I think this is actually a fun example. So it's a weird system. It's a mass connected to the spring and the damper, but then the other side of the damper is actually vibrating. So we want to derive how much force is transmitted from this base excitation to the support. Okay, so we need to, that means your output is your force transmitted, and then your input is the base excitation y. So what is this Ft? According to the definition, these Ft should equal to the spring force, right? So that means your Ft is Kx. Okay, so what we need to do is just find, then we just need to connect X and Y. So what we can do is we pick this M mass out and then draw a free body diagram. So we have a spring force, F spring. We have a damping force, Fc. You have the freedom to choose the direction of these forces. But then once you choose the direction, then you have to be really careful about the sign. Like for example, your Fs. So your Fs definitely equal to Kx. But then is this positive or negative? So that all depends on the direction you define, because we define the positive direction to be pointed downward. And then if you look at these system, when your axis is increasing, we actually have more force pushing it down. So this should be positive. So then let's focus on Fc. Your Fc is c times the relative velocity. Right? Because your c is connected to two moving parts. So the relative velocity determines the damping force. So we define the positive direction to be upward. Let's see. So once your x is moving up, it actually drags your mass down, right? So that means your positive velocity x actually reduces the Fc. And then your positive y is actually increase the Fc. So that's why we need to put a negative sign. Because your x dot should have negative effect on Fc. Your y dot should have positive effect on Fc. So that's why it becomes minus Cx dot plus Cy dot. Okay, so we have Fc minus Fs equals to the acceleration. And then we can plug everything back. Your Fc is minus Cx dot plus Cy dot minus Kx. And then, of course, we move all these things related to x to the left-hand side. And then, again, we want transfer function. We want output and input as ft and fy. Ft is not that straightforward. So we can apply the chain rule. So ft over y equals to kx over y. It becomes k times the ratio of x over the ratio of y. Let's put all the ratios in. So that's why, in order to get the final transfer function, we can directly derive the displacement transmissibility. So easily we can apply Laplace transform. So mx double dot becomes s squared mxs plus csxs plus kxs. And then on the other side is csys. Again, move things around. We have xs over ys equals to cs over ms squared cs plus k. And then in order to get this amplitude ratio, we replace s by omega j and then calculate the norm. So cs becomes c omega j. Your s squared becomes minus omega squared. So m omega squared minus plus k plus c omega j. And then you need to calculate the norm. And then the norm is just c omega, looks like a W, c omega square root C omega squared, the square of the imaginary part, square of the real part, and then take a square root. Okay, you remember this is your x over y. In order to get your ft over y, you just multiply these by k. So you put a k on top. So that means in the exam, I might give you weird systems like this. So whenever you see a system like that, don't worry, because you cannot find any established transfer function in lecture notes. But what you can do is you can start from the scratch. You first derive the equation of motion. And then from the equation of motion, you do Laplace transform to get the transfer function. And then from the transfer function, you replace s by omega j to get a complex number. And then this complex number has both amplitude and phase information in it. If you only need to get the amplitude, what you do is take the norm. If you need the phase, then you calculate the angle. All right, so any questions? Okay, so I move to the last one. That's something you're already seeing during the last lecture. So we have a big mass moving up and down, and then on top of the mass, we have a small ball rotating in constant speed. And then because of that rotation, we have out of balance force or unbalanced force. So the first thing you should do is write down the transfer function. Or if you want, we can start from the equation of motion. You remember that on your right-hand side, that's actually harmonic excitation, right? This F naught is defined as the so-called unbalanced force. So this is your F naught. And then according to definition, your M naught is M naught E omega R squared. So let's see what we already know. We know that the total mass of that machine, M, is 120 kilogram. We know the damping coefficient is 500 kilogram per second. We know the stiffness of the mount is 800 kilonewton per meter. We know MCK. Okay, so what else we need? Okay, we know this unbalanced force. We know that F naught equals to M naught E omega R squared equal to 374 Newton. And then we know the running speed is at 3,000 revolution per minute. So again, we need to transfer these units to radian per second because that's the standard SI unit. So 3,000 revolution, one revolution is 2 pi or 360 degree. 1 minute is 6 seconds, right? So from here we get what that rotation speed is. Let me see, 100 pi. So that means we already, so from there we can get our omega n, omega r is 100 pi radian per second. So what else we need? So we need to define the amplitude of motion due to the out of balance force. And we want to know that if this M naught is 1% of the total mass, so what is E? Actually, the second part is much easier because once we know M naught is 1% of your M or 1.2 kilogram, Then we have m naught, we have omega r. We just plug these two values back into this equation, right? And then we can derive for your E. E is F naught over m naught omega r squared. So we tackle the second part very easily. So how about this? The first part, we need to determine the amplitude of motion. So in this case, that means the amplitude of x due to this out of balance force. Okay, so because it's displacement versus force of an unbalanced rotation, so we already done these in class. So what you can do is you go back to your lecture number 9, and then I believe is on slides 8 and 9. So from there, we have the transfer function. Let's directly copy it. So that means your amplitude x is m naught E m r squared over 1 minus r squared plus 2 zeta r squared. Okay. So again, r is omega over omega n. Or in this case, your omega is actually the rotation frequency omega r. We know that is 100 pi. Your omega n is just simply k over m. So we can easily find this r value. So, but how about these? How about these coefficient here? We don't have this information at the beginning because here for part A, we don't have these assumptions. So we cannot say your m naught is 1.2 kilogram, but we can do a magic. So what we do is we multiply both the top and bottom by omega r squared. And then you figure out that after doing this magic, this part becomes F naught, which is already known. And this part is also known because we know the rotation speed, we know the big mass, right? So that means even without knowing your E and small m naught, we can still calculate your amplitude x. Let me see. Was this the solution? I think I posted it online. I don't have it right now by hand, so you can check it out. So any questions about the unbalanced rotation? So, all right, that's it for today. And I'm gonna post this video on YouTube very soon.